In this video, we'll dig a little deeper into what happens with second order linear ordinary differential equations. For now, we will restrict our attention to second order linear differential equations, which are homogeneous, meaning the right-hand side is equal to 0. Turns out from the theory, the general solution of that type of differential equation always has that form, c1 y1 plus c2 y2, where y1 and y2 are linearly independent solutions. Now, the concept of linear independence is a very important concept in connection with this topic, and that concept can be defined in various ways. If the student has already had linear algebra, the student will have certainly encountered the concept there, and it's really pretty much the same idea here as it is in linear algebra. I'll say a little more about some linear algebra connections shortly. That may be helpful if the student has already had linear algebra and remembers the concept of linear independence there. In practical work for us, most of the time in differential equations, this is the test that we're going to use as given in this box to test whether two functions are linearly independent. I'm just going to quickly introduce the test and how this works, and on the next slide, after we look at some examples, I'll say a little more about where this is all coming from. The test, usually what we're going to do to investigate whether we have two solutions that are linearly independent, the test is going to be, we're going to investigate this 2 by 2 determinant, and I am assuming, whether or not the student has had linear algebra, I'm assuming that people have encountered this formula for the determinant for any 2 by 2 matrix. And the Wronskian, is what this thing is called, is a determinant of this 2 by 2 matrix here. And if you have two solutions, you can calculate that Wronskian. If that Wronskian turns out to be not 0, then that tells you that your two functions are linearly independent. Again, there are many other equivalent ways of defining this concept, but for our purposes in differential equations, this is probably the most straightforward way to get at what we want. So at this point, I would encourage viewers of this video to try creating the Wronskian and calculating the Wronskian, and then think about what it means for each of the three examples that we watched in the previous video. In example 3, we had the differential equation y double prime minus 25y equals 0. We said the general solution had that form. More generally, backing up to example 2, we had y double prime minus k squared y equals 0 for our differential equation, and we said that differential equation had that form. And our first example, example 1, we had y double prime minus y prime equals 0, and we derived the solution of that using reduction of order, and we came up with c1 e to the x plus c2. Now, in this situation, the way you want to read this is you want to think of that as y1 is e to the x. That's one solution, which you obtain by taking c1 equals 1, c2 equals 0. Another solution, which is hopefully going to be linearly independent, comes from this term. If you take c1 to be 0 and c2 to be 1, that gives you y2 equals 1 as a solution also of your differential equation in example 1. So there's 3 examples. I would encourage people watching this video to stop the video right around here and try setting up the Wronskian and calculating it, and then think about what it means. That will be done in detail on the next slide, but I would recommend folks stop the video here and try that on their own before proceeding. Hopefully at this point people have tried setting up the Wronskian and calculating it for those 3 examples. In example A, y1 is e to the 5x and y2 is e to the minus 5x. Plugging those functions into our Wronskian formula and taking the derivative of y1 in the first column and the derivative of y2 in the second column, we get that expression for the Wronskian, that 2 by 2 determinant, and then using our standard formula for the determinant of a 2 by 2 matrix, we get minus 5 minus 5. The e to the 5x and e to the minus 5x cancel out both parts. So minus 5 is minus 10. Turns out to be the value of the Wronskian in that example. So the conclusion is, what that tells you is that the Wronskian, sorry, a little bit of scribbling going on there. So that tells you the Wronskian's never 0, so your 2 solutions are linearly independent. Example part B is almost the same thing, just with a general value of k instead of just -5, and pretty much the same thing happens. If you have y1 is e to the kx, y2 is e to the minus kx, plug those expressions into the general formula for the Wronskian, take the derivative of y1 in the first column, take the derivative of y2 in the second column, use your formula for the determinant of a 2 by 2 matrix and get minus k, so minus 2k for the Wronskian for that example. And we are assuming at this point that k is not 0. So if k is not 0, your Wronskian is not 0, and your 2 solutions are linearly independent. In example C, we had y1 was e to the x, y2 was 1. Plugging those into our formula for the Wronskian, y1 and y2 are in the first row, then we differentiate going down each column. The derivative of e to the x is e to the x. The derivative of 1 is 0. Then we calculate that 2 by 2 determinant in the usual way and get minus e to the x, which is never 0. So our Wronskian is not 0, and our 2 solutions are linearly independent. For a little bit of context and explanation of what's going on here, the student hopefully has encountered this important theorem from linear algebra. It's usually stated in much more general form than this, but for now we only need the form of the theorem for a 2 by 2 linear system. The fact that a 2 by 2 linear system has a unique solution, in this case for x, y is what we would be solving for. That system has a unique solution for any right-hand side if and only if the determinant of coefficients is not 0. If the student has encountered the concept of the inverse of a matrix, another way to think about what's going on here is the system has a unique solution if and only if the coefficient matrix on the left-hand side is invertible, which is the case if and only if the determinant of that coefficient matrix is not 0. So that may help make some connections with the relevant topics from linear algebra that are essentially feeding into what we're doing here. So if we take that linear algebra theorem and think about that in this setting, if we have any second order linear homogeneous differential equation with two initial conditions, y of a is k1, y prime of a is k2, the general solution, as has been stated previously, always has this form, c1 y1 plus c2 y2, and the idea, just like we've seen in the examples that we've looked at, is to then solve for c1 and c2 by solving those two equations which came from your two initial conditions. And that is a linear system, two equations and two unknowns for the unknowns c1 and c2. We want that system to always have a unique solution for any right-hand side k1, k2, and from the linear algebra theorem, which we just reviewed over there on the left in red, that system has a unique solution for any right-hand side if and only if the determinant of coefficients on the left-hand side is not 0, and the determinant of coefficients of that system is precisely the Wronskian. So that's why the Wronskian and linear independence are so important in connection with this topic in our study of linear homogeneous differential equations.